The idea of encapsulation is about containing the elements of an object, not just to keep them together, but to also protect them.
Ow.
We bundle an object's attributes or data along with the methods that operate on that data within the same unit, the same class. One reason for doing that is to restrict access to some of the object's components.
Like how you're restricting me from taking a cookie?
No, you can have a cookie, but you'll have to use my method to get to it. My cookie jar class has an attribute that represents the number of cookies in the jar. When I create an instance of my cookie jar, I don't want you or any other part of my application to be able to reach in and directly change the number of cookies.
Oh, come on. You can trust me.
It's not only about trust. If I let you directly change things, like the number, you might unknowingly change it to something invalid. Like a -1. That value doesn't make sense for the number of cookies and might cause my program to crash. Another reason to restrict access is that, well, maybe I want to limit the number of cookies you can have.
Whoa, no, I don't like the sound of that. So what do I have to do to get a cookie?
Well, to control access to that attribute, I'll hide it so that it's only accessible from inside the cookie jar object Well, to control access to that attribute, I'll hide it so that it's only accessible from inside the cookie jar object itself. Then, I'll add a method called requestCookie that can be accessed from other parts of the application. When you use a requestCookie method, you'll get a cookie, and the method will modify the number of cookies attribute accordingly. One of the principles of encapsulation is that an object should not make anything about itself available except what is absolutely necessary for other parts of the application to work. This is a concept referred to as black boxing. I'm closing off the inner workings of the cookie jar and only revealing specific inputs and outputs. You don't need to know how the request cookie method is implemented under the hood to use it.
But I'm an engineer. I need to know how everything works.
Do you know how your phone works?
Well, sure. I just punch the number into the keypad and it makes a call.
Do you know how it works internally?
Well, you
It doesn't
see,
matter. If you get a new cell phone, the inner workings can be completely different, but it has the same buttons to press, so you can still use it. One of the main benefits with object orientation is that it allows us to more safely change the way the object works without changing the rest of the application. We'll use it. One of the main benefits with object orientation is that it allows us to more safely change the way the object works without changing the rest of the application. Perhaps when I first wrote my cookie jar class, I represented the total number of cookies as a single value. Then, later on, I decided to use 3 separate values to keep track of each type of cookie individually. Since values to keep track of each type of cookie individually. Since I hid those attributes, I don't have to worry about breaking the other 20 parts of my application that have been using the request cookie method to grab cookies. I'll just need to modify the request cookie method in a class to handle the change.
well, if you're the person writing these classes, why would you want to hide your own code? Why keep secrets from yourself?
It's not about being secretive. It's about reducing dependencies between different parts of the application. That a change in one place won't cause a domino effect and require multiple changes elsewhere. That a change in one place won't cause a domino effect and require multiple changes elsewhere.
Then how much should you hide?
Well, different languages have different levels of support for hiding properties and methods, but the general rule is to encapsulate as much as possible.
When I need to create a new class, it may not always be necessary to build it from scratch. If my program has an existing class that's similar to what I need, then I can use inheritance to base my new class on that existing one. Inheritance enables a new class to receive or inherit the attributes and methods of existing classes using the same implementation, which is a great form of code reuse. Let's say, for example, I want to model the characters present in a bakery. I might start by defining a class for customers, which has attributes for the customer's name, phone number, email address, and a customer ID number. Additionally, I'd give that customer class a method to update their contact information and a method to purchase items. The bakery also has employees, so I create an employee class with attributes for the employee's name, phone number, email address, and employee ID number. The employee can update their contact information, get promoted, or retire. Now, looking at these two classes side by side, you might have noticed that they have quite a few similarities. Employees and customers both have a name, phone number, email address, and a method to update their contact information, which are things that are common to all people. So, rather than defining those attributes separately in each class, I can create a person class with all of those common attributes and methods, and then base the customer and employee classes on it. The phrase to use here is customer inherits from person, which means the new customer class automatically gets everything in the person class, all of its attributes and behaviors, without having to write any extra code. From there, I can add any additional attributes and methods that are unique to customers and employees. By convention, if I'm drawing a class diagram with inheritance, I'll use this style of an arrow to show the relationship between these two classes and indicate its direction. The term that's most commonly used for this relationship is that the person class is the superclass, and the new customer and employee classes are subclasses of it. You'll also hear these described as the parent class and the child class, which is typically used when there's only a single level of inheritance, or the base class and the derived class, which better captures the concept of inheritance that's multiple levels deep. That said, there's no limit to the number of child classes I can create based off of a single parent. If I later realize my shop needs another class for the courier that delivers packages, that's easy to add. I'll just create the courier as a subclass of person and give it a unique method to deliver packages. In addition to benefiting from code reuse, the great thing about inheritance is that if I make a change in a superclass, it will automatically filter down and affect all of the subclasses. So, when I realize I should have been keeping track of each person's email address all along because it's the 21st century, I only need to add that attribute to the person class, and then the customer, employee, and courier classes will all get the email attributes too. Changing code in one place is much easier than having to change it in 3. Now, a few languages like Python and C++ allow you to inherit from more than one superclass. Now, a few languages like Python and C++ allow you to inherit from more than one superclass. Now, a few languages like Python and C++ allow you to inherit from more than one superclass, bringing in attributes and behaviors from multiple other classes. However, multiple inheritance can get confusing, so it's much more common to see single inheritance, where a subclass only inherits from one parent or superclass. Languages like Java, C#, Swift, and Ruby enforce single inheritance with classes, and that's what we'll be using in this course. Our fourth and final object-oriented concept is polymorphism, which is a complicated sounding word that simply means having many forms. And is polymorphism, which is a complicated sounding word that simply means having many forms. And appropriately enough, there are multiple forms of polymorphism. One form, called dynamic or runtime polymorphism, allows us to access methods using the same interface on different types of objects that may implement those methods in different ways. Think of this basic coffee maker as a class with a method to brew coffee. The input parameters for that brew method are a scoop of ground coffee beans and water. I wait a bit for it to brew, and the output is a fresh cup of hot coffee.
I prefer to use a different type of coffee maker, a French press. My French press also has a brew method with the exact same inputs and outputs as Barron's basic coffee maker. I input a scoop of ground coffee and some water. Then after a little while, I press down the plunger and the output is a fresh cup of hot coffee.
Now, although these two coffee makers have the exact same type of inputs and outputs, the way that they brew is very different. My coffee maker uses a filter, whereas Olivia's French press strains the coffee with a metal screen.
And although the outputs we received are the same type of object, a cup of coffee, their attributes may have some different values. When it comes to taste, my French press coffee is better.
Now, when it comes to actually implementing this type of polymorphism in code, there are several ways it could be done. Olivia's fancy French press could inherit all of the attributes and methods from my basic coffee maker. but then it replaces the brew method it inherited from the basic coffee maker through a process called overriding. That allows the French press to redefine its own unique version of the brew method.
Or perhaps both of these coffee makers inherit from the same abstract class with an abstract brew method.
Or they both agree